And as far as I know, we have got some questions regarding to Professor Geratov's talk, and also we are open for any kind of question related to Professor Morgan's talk, even since there was not too much time to complete with the biomedical 3D printings, release issues. So we can also discuss some details about this issue. Anyone who is present can ask questions, and I guess that we have already three available. Don't hesitate, please.
Shall I break the silence and
Yeah.
pick one of those questions which I got for my presentation? Is that a good idea?
It is.
Okay, so JPFM, which is not really a name, I guess, but asked the question about, can you please give an example of gamma rays being used in 3D printing? That's the first question which I got. And actually, it's a hard one, because to be honest, providing an example is something which I can't do. The reason for that is that I think this reference to X-ray and gamma ray initiated photocuring is actually originating from the very first patent of Chuck Hull. And let me explain a bit about patents for understanding my answer. When someone writes a patent application, then the major goal is to protect the technology to be patented from fraud. It means that the applicant does not need to demonstrate all statements in the patent. However, if they can demonstrate the key steps and require protection for related fields, that's a very typical way of filing a patent. And what my guess is that when Chuck Hull applied for his patent in the 1980s, he already got very nice results regarding UV curing, but did not demonstrate the process for X-ray and gamma rays, which are typically much lower wavelength part of the electromagnetic spectrum. I don't know whether it's a good idea or not to try to share an image now. Yeah, probably. Okay, no, I can't. Anyway, what we are talking about is that the UV light typically has something like a 10 to the minus 8 meter wavelengths, while X-rays are typically 2 orders of magnitude, and the gamma rays are even further 2 more orders of magnitude shorter in wavelength. And why is it important to use a radiation which is shorter in wavelengths? Because there is a general physical process which actually states that the resolution is inversely proportional to the wavelength. So if we have a shorter wavelengths, we can resolve finer details in the resin. And I think that was the idea why they actually placed and received protection within the patent for other wavelengths than UV. However, the feasibility of curing at these ultra short wavelengths has already been demonstrated. So that is there's a wide field detailing how these resin material are behaving at X-ray and gamma ray radiations. The only point which I cannot really provide as an example whether gamma ray sources were really used in a 3D printer. So that was my first question. Shall I proceed or let someone else to ask something?
We'll just go ahead and
Go ahead.
so to
Okay.
speak.
Well, the second question which I got is about is from Uma Shukriti, who asks, "Can you please tell what kind of materials are used to make 3D organs?" 3D organs are made by bioprinting, and for that, as I mentioned, you basically need two major components, something that will form the scaffold, and the other which will provide the living material. Regarding living material, we usually use cells directly taken from the patient or treated by various biomedical means. Very common concept is using stem cells, especially after so-called reprogramming, which is called pluripotent stem cells. And these cells also need so-called growth factors in the mixture to help them to differentiate in the proper way, so form a bone or form a cornea or a skin. So one component of bioprinting is actually coming from these biological and bioorganic materials. The other component, the scaffold, is a bit trickier to answer. There are several scaffold materials, for example, like collagen, which will provide a structural stability for the 3D object and can be used in a petri dish, so in vitro. However, cannot be transferred into a patient. So it's a good idea to ask why is that interesting if it cannot be transferred into a patient, because some of these 3D printed biostructures are used for drug testing and drug development and similar things, and only some of them are actually made for regenerative medicine to put into the patients. Making a scaffold which is also transferable into a patient is an actively studied field, and there is no general solution to the problem. However, there are a few working examples in which the scaffold can already be put into back into the patient. So that's the second one. And yes, what are the main, okay, sorry, Iona Marika had a question about what are the main challenges of 3D printing for biomedical applications? Well, this is a very, very good and a very big question at the same time. For biomedical applications, if you think about bioprinting, first of all, then bioprinting is less of a challenge in terms of building the structure. So it's a composite structure with scaffolds and living cells and factors and macromolecules. So making them is less of a challenge. What is a real challenge is to promote the growth and differentiation of the structure into a living tissue or even into a living organ. And that's something which is a very challenging, but unfortunately I can't really say too much about this because this is not my field of expertise. I'm a physicist and I've learned a lot about these, or hear a lot about these, about some of my colleagues, but I'm not really an expert to answer that. But one important issue in this keeping alive challenge, keeping alive the structure what have been built, is that the structure need to be fed in order to grow, differentiate, and so on. And every time when we are beyond a few hundred micrometers in size, the material transfer within the structure is not easy to realize. In nature, nutrients are usually delivered to the cells by blood vessels, but building and making vascular structure is not yet solved by 3D printing, so we cannot rely on blood, a similar structure like a blood vessel for material transfer, and every other means is quite a challenge to realize. Yes, and my last question is again from Uma Sukriti, who also asked about, are the used 3D materials biodegradable and its effects on, and what, I guess, what its effects on the environment? The answer for that is that yes, there are a few precursor material which is biodegradable, but most of the material used are not. However, in the last 10, 12 years, there are efforts in this area. So more and more people are realizing that if we're going to use 3D printing as a real manufacturing technology, we need to take care of the wastes, and we also need to take care of the environment. So this is something which is under study at the moment, but this is not a prerequisite for every single material we use. Most of the material do not degrade, but there are a few, for example, FDM filaments are dedicatedly made from biodegradable materials. So that's a good point, that we have at least a few examples in this regard. That's all what I got.
Okay, so may I add also some notes to the question you started to explore, which was about the bioprinting. So I guess that there are a lot of advantages, at least possibilities and potential advantages. So if we build up something from the patient's own tissues or own cells, it can be put back without any risk of autoimmune response, tissue rejection. And I don't know whether the audience knows that all the transplanted people during their entire lifetime have to be immunosuppressed, which is a huge risk for the everyday life. Unfortunately, our tissues are growing continuously in an environment which is full of challenges. And these challenges are either environmental challenges, since Professor Gertus mentioned bioprinting of cornea or skin, And in this case, the challenge is the non-sterile environment. Until the tissue is grown in a dish, we can keep it in sterile environment. But if it is transferred to the human body, sooner or later it has to be exposed to the normal environment, which is full of bacteria, fungi, etc., etc. So therefore, it is very difficult to make a good and safe transfer. With the internal organs, the problem is especially with the muscle, like the heart, that it should be trained before it is put into a living person. So since our heart has been trained for the very beginning of our life, so untrained, the heart cannot be replaced, cannot replace the existing one. Maybe one of the easiest tissue could be the liver, because the liver has a very good reproducibility, and it is quite homogeneous. And also some of the hollow organs like urinary bladder or some other hollow organs can be put back to the living host without too big risk of rejection or contamination. So, any other questions regarding the two talks this morning? You can write it down, or you can just switch on your mic and speak it.
What are the latest experiments that they are doing
Sorry?
regarding? Can you hear me?
I cannot hear you.
Cannot? Okay, I'm gonna write it.
So, even you can ask questions regarding this entire week, not because we can answer the specific questions, but about the summer school, about structure, about the content, which was the most easy to follow and which was the most difficult one. What are the latest experiments that are aiming at 3D printing technology? Uh-oh. Can you answer this question? Go on.
Well, thank you, Mr. Chairman. My next presentation gonna focus on the latest advancement. No, but honestly, this is a very wide topic. So answering that question is basically means that I should pinpoint a few recent results which are related to 3D printing, because what we are talking about is that roughly about 200 academic and industrial centers around the world are developing additive manufacturing technology seriously. So this is not the number where 3D printers and printers are used, but these are the sheer number of places where academic work and product developments are seriously considered. So one example from the not too far past is that a few years ago, General Electric was the first company who actually demonstrated its interest, its serious interest towards 3D printing. GE is actually has a very wide portfolio of technologies, and where they saw the first possibilities was aviation. And actually, they started to work on using 3D printing for making engines, aeroplane engines. These are big, very complex, very efficient, sensitive instruments. And what they saw, roughly something like 10 years ago, is that there is a huge potential in using the key benefits of additive manufacturing and transforming it to real benefits into these engines, turbo engines mainly. And just one thing, so they actually started to produce, I mean, in serial production, a key component of these engines a few years ago, by which they were able to reduce the mass of the engine, increase the efficiency, reduce the fuel use of these engines. And by now, there are already aeroplanes on the market which actually run such engines, and they started to. So the investment what GE put into this has already started to flourish, and as a result of that, they decided to cross-fertilize the whole portfolio of General Electric with 3D printing, and they formed a new company called GE Additive. They actually bought manufacturers, 3D printer manufacturers. They already started to buy supply companies making powder, for example, for themselves. And this is the biggest industrial success of AEM by far, as much as I know. This is one example. Another example, which is much closer to biomedical applications, is and came into mind, is that in April this year in New York, the first site was opened by Lima Corporation, an Italian company originally, and their site is actually servicing implants and surgical instruments to New York Hospital, and I think it is called Hospital of Special Surgery. So basically, this is the very first site in the world where CT images from the hospital actually transferred to the 3D printing center, and on site they are printing out the required patient-specific implant in a controlled and accredited way, which the doctors can use a day or two later during the surgical operation. That's another example. But if we also leave the medical side for a moment, automotive industry is also a field where 3D printing is vividly used in the recent years. In various parts of the cars, they can benefit from building a cockpit in one piece is something already demonstrated. More convenient seats are also built by BMW, by 3D printing, and so on and so on. So plenty of things are running in the backgrounds or backstage. Experimentally, one of the key areas where further development is needed is increasing printing speed. So the reason why I mentioned the clip technology by Carbon 3D was partly because of this, because even if you know photo curing or the basics of photo curing, you need new elements, key improvements to the process in order to reduce the build speed from several hours or maybe a few tens of hours down to the hour scale, so to say, because there are some critical applications where the part is needed much quicker than how fast it can be delivered nowadays. So there are fundamental fields to improve, and there are also application-oriented developments where 3D printers are intensively used nowadays.
Okay, any other question? If not, I guess that we can conclude that with a great session, and we have gained a lot of new information. Metal, how can, okay, how can you count with expansion? Can you see the question?
Yes, I do see the questions. Thank you. I don't know what expansion you actually think of, but I guess that you're probably thinking about the difference in density of the molten material and the resolidified material.
This thermal expansion.
Exactly. This is what I also mean. So one good thing of laser-based manufacturing technologies in general is predictability. And this is not unique to metal 3D printing, but this is something what is routinely realized in laser cutting, laser welding technologies as well. And since, and it means that when you do know that you would like to build a wall with a 1 millimeter width with a certain tolerance, and you do know that you need to melt a little bit more, bigger area in order to achieve this size after cooling down, you can incorporate this extra irradiation into the program. It is done in a way that when you are setting up your printer, you need to perform several so-called calibrations. And some of these calibrations with every technology is aiming to correct dimensional inaccuracies, or so to say, tune the accuracy of the machine to achieve the best possible resolution and the smallest possible tolerance. So you can imagine this as it happens that you have a standard sample, the size of which you know precisely with by varying the different parts and dimensions, and then print it out and you take out the sample from the printer and measure the size. And if you are lucky enough, and most of the time with metals you are, if there is a linear correlation between the printed size and the aimed size, then you can simply take a factor or derive a factor and modify the computer program according to that factor. Sometimes the process is not linear. For example, with photolithography, it is typically not linear process. Then you repeat this process with several samples, several exposures, and you derive a nonlinear correlation between or a function between the desired and realized size, and you need to take into account during the setup of the printer. So yes, it does happen, but the good news is that the process can be corrected for that.
Thank you. Any other question? Okay, if not, please keep in mind that there is a test session in the afternoon. So for people who are assigned for credits, there will be a test exam, and please look at the talks, because all the questions are related strictly to the talks given by the experts during this week. So thanks for attending, and wish you very nice weekend and enjoy your summer. Thanks again. Bye bye.
Thank you very much. Bye.